Hi, AP Chemistry. Welcome back to kinetics. This is part 3. So last video, we talked about the differentiated rate law. So this lecture, we're going to talk about the integrated rate law. Now, again, the integrated rate law it's the same description, right? We take the rate law that we've been working with, especially last class, and basically we're taking that equation and we're integrating it. So it still represents the same thing. It can still represent a zero order reaction. It can still represent a first order, a second order. That's going to be our scope, though. The integrated rate law, it takes a different form depending on the order of your reaction. And so we are only going to deal with the forms for 0, first, and second. So those are going to be the 3 that you are responsible for knowing. Now, others can exist. There's also a pseudo first order rate that can exist, but the scope that we're going to deal with is going to be for 0, first, and second. Okay, so basically, the way that we integrate rate law is we're going to take our normal rate law that we're used to dealing with here, and then we're going to change it into y equals mx plus b form. So in order to get rid of the exponent there, you have to unexponent the whole equation. And so as you can see, in the case of this one, that results in a natural log being introduced. If you take the natural log of both sides, all the pieces kind of get separated from each other. You know, the K gets separated from the concentration, and it gets reorganized into a form that can represent a graphing equation. So we can reorganize this integrated rate law into the y equals mx plus b form. Okay, now just a side note here. Usually we show you how to get from one form of the equation to the next, because my soapbox is always, it's better to understand the logical process than it is to just flat out memorize a whole bunch of equations. But in this case, it's actually not. So we're not going to step you through the integration that takes place from the first to the second. If you're currently in calculus, this would be a good thought experiment to go through, is try and integrate that form yourself and see if you can see how they come up with the integrated rate law. If you're not in calculus yet, you can look forward to this in the future. And honestly, it's not worth our time. It's not worth our time to walk through how to do this. It's a better use of our time just to memorize these equations. And actually, these equations are on your reference sheet. So the best use of our time would be to go look at our reference sheet and go find where these equations are. Now, as you do this, you will notice that on your reference sheet, the integrated rate law forms are not actually listed in the y equals mx plus b form. But as you'll see, we draw heavily from the graphed form of the data in order to draw conclusions as to what the order is. And so another great use of your time would be taking the form of the integrated rate law that's on your reference sheet right now and working it out yourself into the y equals mx plus b form, so you are comfortable doing that. The y equals mx plus b form is very important. You want to be able to tell me what the slope is, what the y-intercept is, what your variables would be for this graph. So take a minute, make sure you go do that at some point in time. Okay, so a couple things to note off of the integrated rate law. Now, first of all, this is the integrated rate law for a first order reaction. This is not the integrated rate law for zero or second order. It is specifically for a first order reaction. So this M would have been replaced by a 1, and then the whole shebang was integrated. And this is the format that comes out of that. Notice that rate is gone, right? This is no longer a relationship between rate and concentration. That's the relationship that's communicated through the differentiated rate law. The differentiated rate law shows the relationship between rate and concentration. The integrated rate law does not. What does the integrated rate law show a relationship between? And if we look at y equals mx plus b, if we look at it in terms of this, we'll notice that the y is still concentration or some form of concentration. In this case, it's the natural log of the concentration, right? X is t, it's time. So the integrated rate law is no longer a relationship between rate and concentration. It is now a relationship between time and concentration. And so, like we talked about yesterday, this can have pros and cons. The pro being it's a much easier to track time in a reaction than it is to track rate. And so that is a huge benefit of being able to use the integrated rate law. We can just track time as one of our variables, concentration as the other one, and it's going to be a much easier experiment to run. Okay, a couple other things to notice off of this integrated rate law. If concentration is y and x is time, then slope is going to be negative k. So on this graph, your slope should be a negative k. Okay, so let's take a look at how this is used. Okay, if we were to collect data, time versus concentration, and graph it, we should get a straight line if we graph natural log of A versus time and its first order. So this is one of the ways, this is one of the methods we can use to figure out the order of the reaction. We can graph it a whole bunch of ways. One of the ways is going to be natural log of concentration versus time. So probably this way maybe. And if on this graph we get a straight line, we know that the reaction is first order. Now, what will our other two graphs be? Well, one is going to represent the y and the x for a zero order reaction. One is going to represent the y and the x for a second order reaction. So when we talk through zero order and second order reactions, I'll tell you what those graphs are. All right, so for example, here is a reaction. We have a decomposition of N2O5 dinitrogen pentoxide. They collected some data down here, and notice that the data is in terms of concentration versus time. So we could not use this data as the method of initial rates because we don't have any data off of the rate, right? We have an initial concentration, and then as the reaction proceeds forward, 0 seconds, 50 seconds, 100 seconds, so on and so forth, we can see the concentration drops and drops and drops and drops. So this is not a method of initial rate reaction or experiment. This is not multiple trials. This is one trial where we watch the concentration drop as the time proceeds. So there's big differences between the setup for this experiment and the setup for an initial method of initial rates experiment it would be worth your time to set up kind of a Venn diagram and sort out what are the differences between the two experiments and what do they have in common. So again, we can't use this data in the same way that we use the method of initial rates data to figure out what the order is. We have to use a different method to figure out what the order is. And basically the method we use is going to be the graphing method. So in order to verify that the rate law is first order, we would graph this time versus natural log of concentration. So let's see what that looks like. Okay, so here is a graph of time versus natural log of concentration, and you can see that it's fairly straight. It's not a curve one way or the other, right? It's a fairly straight line. And because this specific graph is a fairly straight line, we can conclude that it's a first order graph. It's a first order reaction. Okay, now, how would we, the second thing that this question asks us to do is to calculate the value of the rate constant. So we know what our rate law would be, right? A general form would look like N2O5 M. We now know what the order would be, so we can fill that in. N2O5 1, right? In order to complete this rate law, what we need now is the K. We need the slope. So we can do this in a couple different ways, but one of the ways would be to look at the integrated rate law and use that to calculate out an answer. So if we go back, okay, here's our integrated rate law. Natural log of A equals negative KT plus natural log of A to the naught. Okay, so let's look at these variables. Remember, we're going to solve for K. So basically, we want to plug in values for everything except for K. So what is this A concentration and what is this A naught concentration? So A naught is going to be our initial concentration of A. So this would be natural log of 0.1. Negative K, we want a value for T, equals natural log of A. Okay, so the A and the T are going to correspond to each other. If you choose 100 for your T, that means 0.05 is going to be your A. If you choose 400 for your T, that means that this 0.00625 is going to be your A. These two have to go together. So let's just do the bottom one in hopes that as the reaction proceeds, we're going to get more consistent results. So we'll go natural log of 0.00625, and then the T we're going to plug in is 400. And now we can solve for all of this. So you take your little calculator, and in this case, you do need a scientific calculator, unlike my cute little calculator that comes on my phone. Okay. Make sure you're using the natural log button, the LN, and not the log button. The log has a base of 10. The natural log has a base of E. Different functions. Okay, so according to my calculator, who knows if this is right or not, 0.00693 equals K. Did anybody else get that? Hopefully. Okay, so 0.00693, let's assume this is correct. Now, 0.00693, what? We need units on K. K has units. So getting the units off of the integrated rate law is madness. So again, it's much easier if we look at the units off of this normal rate law. And so we can see we want rate to be molarity per second, right? We need K to be something, and since this is concentration to the first, it's going to be times molarity. So something times molarity has to equal molarity per second. So K has to be 1/second. So we can put the inverse of seconds here and box it, and that's our K, which we can now plug in, and we will have a completed rate law expression. Rate equals 0.00693 seconds to the negative first, brackets, N2O5 to the first. That is our completed rate law expression. Ta-da! Okay, so let's take a minute and recap. First of all, the data that they gave us forced us into a method of evaluating it. They gave us data that was time versus concentration and not data that was rate versus concentration. So because they gave us time versus concentration, we have to graph it and compare it to the integrated rate laws to see which one comes out as a first order. So we graphed natural log versus time. It came out as a straight line, so we know it's first order. Once we figure out that it's first order, then we can plug some of our data in to our integrated rate law for first order to calculate out a K. And then we have to figure out what the units of K are, and we can finally write a differentiated rate law that is completed for this reaction. Okay, so now that we've seen the method once, we will practice that together in class. What I want to go back and do now, we've talked through first order, let's talk through zero order and second order. Oh, look at that. They got the same K as I did. I really need to bring TI-83 home so that I get more reliable answers. But all right, calculator on my cell phone came through this time. And note their units, got the same units that we did. Okay, so one of the other things that we can do with this, once we have all of that information worked out, we know that it's first order, we found the K, we found the units of K. Now we can use it as a predictive tool. So at 150 seconds, for example, what would be the concentration of N2O5? So one of the ways we could do this is we could look at the graph, and we could ballpark where 150 would be and try and figure out the concentration from there. That probably wouldn't be a super accurate way. It would give us a ballpark answer. So if that's what we're looking for, we could estimate off the graph. If we want an exact answer, however, we're going to have to use one of the equations. So since the differentiated rate law, again, has nothing in it that relates to time, we have to use the integrated rate law. We know it's first order, so we use this form. We know what our initial concentration was. We know our time is 150. We know our K, we just figured that out, is 0.006 something, 6233293. Here we go. Okay, so we can use this to calculate out natural log of something. Let me do this real fast. Oh, shoot. I don't have a negative button. Okay, wait for it. All right, again, I'm fairly sure this is the answer. This little cell phone makes me put things in a different order. It doesn't make me super comfortable. Okay, so here we are. Natural log of whatever the concentration is, which is what we're looking for. We're looking for the concentration is probably equal to negative 3.34. How do we get rid of the natural log? Oh, math class. Do you remember? Okay, remember we talked about how log has a base of 10 and natural log has a base of e? Well, you use that e to get rid of the natural log. Basically, we're going to take e raised to the for both sides. And if we raise both sides to e, then this natural log and the e reduce each other out, and you're left with an answer. So let's see if little calculator buddy will do this for us. Maybe. 0.0354. Okay, so let's go look and see if this is reasonable. I mean, it's less than our initial amount. That's a good start. So 0.0354. Ugh, let me erase this. 0.0354. Okay, so our answer should be in between these two. Okay, 0.03 would be reasonable. So concentration 0.0354 at 150 seconds. Okay, so again, this is one more thing that you can do with the integrated rate law is you can use it as a predictor of what the concentration would be at a specific time or what the time would be at a specific concentration. But you do have to know how to solve with natural logs. So the little button on the calculator that you're going to use, that E, make sure you're using the lowercase e, not the uppercase EE button. Okay, so make sure you're using the right E. Okay, we'll do this together. And actually, I don't want to do half-life yet. I want to talk through the other forms of the rate law. Do we not have a slide on this? Aha, here we go. Okay. All right, so a zero order would have an integrated rate law that looks like this. So here's your differentiated rate law for a zero order reaction. here's the integrated rate law. Okay, so notice a couple things. Now would be a good time to sit down and do a Venn diagram of the zero order rate law versus the first order rate law, which is this. So they do have some similarities. Notice again, it's in the y equals mx plus b form. Notice again that x is time. Notice again that slope is negative k. So far, fairly consistent. However, your y is not the same. Instead of being a natural log of your concentration, your y for a zero order plot is actually just concentration. So if you graph concentration versus time and it comes out to be linear, then your reaction is a zero order plot. Okay, so zero order is concentration versus time with a negative k slope. First order is natural log of concentration versus time with a negative k slope. Let's look at second order. Okay, we've talked about first order already. Second order, here we go. Okay, so again, you can see our differentiated rate law there with the little 2 indicating that it's second order. And then you can see the integrated rate law below it. So again, x is time. That's a similarity. Again, slope is k. However, it's not negative k. The other two, the slope is a negative k. For this one, the slope is a positive k. And then again, another difference, the y is the inverse of the concentration of A. So for zero order, the y is concentration of A. For a first order, the y is natural log concentration of A. For a second order, the y is 1 over concentration of A. Okay, so they all have a different form, and you do have to know the different forms. Again, they're on your reference sheet. Go look at them. They're just not written in terms of y equals mx plus b, but you should be able to arrange what's on your reference sheet into a y equals mx plus b format. Okay, so if we run an experiment and we want to know, is this experiment zero order, first order, or second order, we would have to make 3 graphs. So we are going to collect concentration of A versus time. That's what we would collect off of a reaction. And then we would take this data and we would make 3 graphs. One of the graphs is going to be time versus concentration. One of the graphs is going to be time versus natural log of concentration. And one of the graphs is going to be time versus the inverse of concentration. And then whichever one comes out linear, that's the order. So one of the 3 should come out linear for most reactions. And then that's going to be the order of the reaction. Whichever one comes out linear indicates that for you. Okay, so we kind of walked through all of this information for first order, but it's really consistent for zero and second. It just has a slightly different format of the integrated rate law. So from these integrated rate laws, now we can go back and look at half-life. So let's do that. This is what I skipped earlier. Okay, so what is a half-life? So we talk about a half-life for radioactive things. The one that you've probably talked about is carbon-14, right? Carbon-14 is a radioactive form of carbon, and every 5,864-ish years, I don't know if that's actually right. It's somewhere around there. Half of your sample of carbon-14 is going to decompose. So if you start with a rock, that's all carbon-14 in whatever this year is. Maybe we should actually look this up. All right, it's 5,730. Hey, that was pretty good. Come on, that's pretty good. Off the top of my head, I give myself credit for that. Okay, so every 5,730 years, half of this sample decomposes into some form of nitrogen. I don't know, it's a nuclear reaction. We don't deal with these things. I think it gives off like an alpha particle or a beta particle or something like that. And half of it is now nitrogen. The other half is still carbon-14. Now, obviously, it doesn't look like that. It just doesn't divide in half. You still have a whole rock present. It's not like, half the rock poofs away into magical sparkle fairy dust, right? You still have a whole rock present. Just half of it is something else now, and half of it is still carbon-14. And again, it's not going to do half and half. It's going to look more like this, where distributed throughout, half of it is now nitrogen and the other half is carbon-14. So this time, the time it takes for half of the sample to decompose into something else is half-life for a nuclear reaction. Now, we can talk about half-lives for a chemical reaction also, but instead of talking about the carbon-14 decomposing into something else, it's talking about the time it takes for half of our reactants to turn into products, or the time it takes for our initial reactant concentration to be halved, to be cut in half. So when you talk about a half-life, you're communicating a time. It's a specific time. It's 4 seconds. It's 100 seconds. It's 5,730 years, right? It's a time. This reminds me of melting point and boiling point. When they ask you what the melting point or boiling point is, you're going to communicate a temperature. Same thing with half-life. When they ask you what a half-life is, you're going to communicate a time, right? So because the integrated rate law is talking about that relationship between concentration and time, it sets us up perfectly to figure out or relate to a half-life. Okay, so we can look at this graphically. If we look at what the initial concentration is of our reactant, the time it takes to decrease that by a half would be the half-life. And then you can have successive half-lives throughout your reaction. Okay, if we look at this in terms of our integrated rate law. So here's our integrated rate law for first order reaction. So we have an initial concentration and we have a concentration at a specific time. If we want to know what our half-life is, we can ballpark some of this information. Like if we make A0 a 1, then the concentration at our half-life of A is going to be 0.5. Or if we make our initial concentration 100, then at the half-life, the concentration would be 50. So sometimes, especially if you know the K, you can actually plug in some generalized numbers here and calculate out what your T is going to be. Okay, so you can see they've kind of done this. They've rearranged the equation, right? From here to here, it's just rearranging the equation so that you get concentrations on one side and time on one side. And then they've done this exact thing. They've plugged in a 2 for your initial concentration and they've plugged in a 1 for your concentration at half-life. And then we actually can, natural log of 1/2 is a real number. That's an actual number. And so what we get is this relationship between half-life and K. So we can actually solve this out. And we get the half-life, T half, equals natural log of 2 divided by K, or you can plug in that actual number of 0.693 divided by K. So as long as you know the K for your reaction and its first order, note, it's a super important note, this is for a first order reaction because we are using the first order integrated rate law, right? Okay, so as long as you know the K for your first order reaction, you can plug it in and actually figure out what your half-life is, which is pretty cool. This is really cool for a chemical reaction because our half-life in this K does not depend on our concentration. So for a first order reaction, as your concentration changes, the half-life actually stays the same. So the half-life at concentration of 100 is the same as the half-life is going to be at concentration of 75 and 50 and 25 and all the way down. The half-life stays consistent for a first order reaction, which makes this very useful. In contrast, if we look at zero order reactions and second order reactions, and we kind of walk through the same thing, what you're going to see is that those half-life equations, they actually are dependent on the concentration. So let's say initially you have 1 mole of your reaction, of your reactant, right? And your half-life is 5 seconds. Well, as soon as your initial concentration changes, your half-life's not 5 seconds anymore. Your half-life will continually change with your continually changing reactant concentration, and that is not a very useful half-life equation. So really the only useful half-life equation is the one for first order reactions. Zero order reactions and second order reactions, because their half-life equations are dependent on the concentration of their reactant, they become kind of useless equations. And you can see that here. So for a zero order reaction, the half-life is dependent on K, but it's also dependent on the concentration of the reactant. Same thing with second order. The half-life equation is dependent on K, but also dependent on the concentration of your reactant. So as the concentration of your reactant continually changes, so does your half-life. So does the time it takes to get to half, which turns meaningless real quickly. So that would be the thing to know about zero order and second order half-lives, is that they're not useful equations because they are continually changing with the continually changing concentration. You would probably have to apply calculus to that in order to derive any meaning out of it, which we are not going to do. On the other hand, the first order half-life reaction is a very functional equation. You should be able to get the time it takes to get to half independent from the concentration, which makes it very useful. Also on your reference sheet, go find it. And this is just a summary of what we talked about before. Okay, here's practice. We'll do together. So now would be a good time to pause and summarize. Each order, zero, first, and second, has its own rate law, its own integrated rate law, its own graph, its own slope, and its own half-life. Can you write these out? Can you fill in this chart? Can you do it from memory? Can you do it with a reference? How functional, how comfortable are you with all of these things for the 0, first, and second order reactions? Again, pseudo reactions exist, but you don't have to deal with them with all of these things. Okay, so we'll start here, do some practice together. Jot down your questions. Let me know what those are. I will see you when we do practice together in class.